What's up, CoderByte? Welcome back to another data structures and algorithms video. I'm Elizabeth, and today we are going to be doing another meta interview question. This is one I was actually asked during a meta interview, and it's a cool problem. It involves some imagination. It uses the two-pointer approach, which we've discussed previously on this channel. And with that, let's get into it. Okay, so this week's problem. It is called the biggest water container. And like I said, it involves some imagination and some visualization. So I've added a bunch of visualizations to these slides to kind of help you imagine what's happening in the problem. So what's the question? You are given an array of integers representing height of length n. There are n vertical lines drawn. So every single element in this array is going to represent a bar on the graph. And each value in the array represents the height of that bar on the graph. So there are n vertical lines drawn such that the endpoint on the x-axis are I and 0. So I is the index, and where the bar is on the x-axis depends on the index of it in the array. And the endpoint on the y-axis are I and array at I. So where the y-axis value is going to be the actual value in the array. So take this array, 1, 8, 6, 2, 5, 4, 8, 3, 7. Each of these numbers are representing the height on the graph, and each element's index represents where it is on the graph on the x-axis. So let's look at that. So we can see here, these are the bars, these are the heights. And if we look at the first element, 1, it is at the 0th index. So 0 plus 1 in this bar graph is going to be 1 at the x-axis, and the height is 1. So we can see that on the y-axis. We do the same thing for the next element, which is 8. It's 2 on the x-axis and 8 on the y-axis, and so on. This is the bar for 6. This is the bar for 2. This is the bar for 5, etc. I worked really hard on those arrows, but I think you guys get the point. Okay, so what is the actual question now that we understand the arguments that we're going to expect for the function? So find two lines that together with the x-axis form a container such that the container contains the most water. Okay, so what does that mean? Return the maximum amount of water a container can store. So let's look at this on that graph. Also notice that you may not slant the container. So here we have our graph, the same array from before, and we can imagine that the bars on the graph form a container. Now, why does the water only go up to the shortest bar? Because if you were creating a container and one side was bigger than the other, you cannot slant the container. That doesn't make sense. You can't fill the container according to the highest side because it would fall out on the lowest side. So ultimately, you have to find the container, which is like which two bars can form a container, where the area can hold the most water. So you can see here that the biggest area of water that we can hold is between these red bars. So why is that? So the shortest side of this container is going to be 7. And you have to take into account for a container the height and its width. So not only is this side 7, but these elements are 7 points away from each other. So the area will be 7 times 7, which is width times height, which is 49. And this is the highest area that we can get. Now, the height of the shorter side of the container times the width between the two sides, which is our formula for finding the area. Now, I want to note, you might think, well, just find the tallest bars, and that's the answer. So let's look at the tallest bars. We have at index 2, we have 8, and at index 7, we have 8. So 8 times 8 is 64, right? But you have to take into account not just the heights, but the width. So 7 minus 2 is 5. So even if we can fill the water higher at 8, 8 times 5 is 40, which is less than 49, which we get with these bars. So, something to think about. So let's talk about the naive approach. Now, when I first looked at this problem to teach to you guys, I actually did the naive approach first. Why? Because often to do the naive approach helps you figure out what the better approach will be. Also, in an interview setting, if you can't get the better approach, at least you're doing something with writing the naive approach. Try not to spend too much time on the naive approach because you want to leave room for figuring out the better approach. But we're going to talk through the naive approach to I'm going to walk you through what my own process was in solving this problem. So the naive approach, to find the largest area between the bars that can contain water, we could naively compare the area between each bar and every other bar. Now, this should, bell, ding, ding, ding. That's going to be a nested for loop. So this would involve a nested loop, but that would give us O of n squared, which we know we want to avoid at all costs. But let's watch that happen. So here we have our graph, and here we have our 2 pointers. So we're going to look at this bar compared with every other bar on the graph, finding its areas, and then ultimately taking the max of those areas. So our first container is going to be the height of the shorter side, which is 1, and the length between them, which is also 1. So the area is going to be 1. 1 times 1 is 1. And again, the formula for the area is the height of the shorter side times the width between the two sides. And then with a nested for loop, what are we going to do? We're going to move our second pointer to the next bar, and we're going to grow our container. So again, the shorter side is 1, but now we have a higher width, which is 2. So that's going to be 1 times 2, which is 2, which is better. Then we're going to move our pointer to 4. We're going to do the same thing. Obviously, the first bar with any of the other bars is going to be limited by the height of the first bar because it's the shortest bar. So again, we're going to do, 1 times 3, and that gives us 3. And, I didn't finish the slides because you could figure out the rest. So finally, we move our first pointer over, and now we're going to compare this bar with all the bars that come after it. We're not going to compare it with all the bars that come before it, because we've already looked at those, right? We've already looked at 1 and 2 together. We don't have to look at 2 and 1 together. So now we are comparing our second and third bar. Our first pointer is at the second bar, and our second pointer is at the third bar. So let's see what happens there. So our lower wall is a height of 6. So we multiply 6 times 1, which is the width. And here we get an area of 6, and so on. We move the second pointer over. We are now looking at a minimum height of 2, and it is 2 away. So we have 2 times 2, which is 4. So, again, I didn't fill this whole thing out, but I think it's pretty self-explanatory. And we are going to code this out. Whether or not you actually do this in an interview setting, again, I really recommend you doing this while you're studying or learning for yourself. It's really useful to think about the naive solution when you're building that optimal solution. So let's do this. Okay, so as usual, I'm in Visual Studio Code, and we're going to start to code the naive solution to this problem. So let's start by defining our function, which is most water, and I'm going to call most water naive because we're going to write the optimal solution, and it's going to take an array, which is, remember, our array of heights. I'm going to put in our test case, which is going to be most water naive, and then I'm just going to copy and paste the array from the slides. Oh, I missed a bracket. Okay, wonderful. And let's do our comment block. And this is going to be takes an array, and this is going to be an array of heights, and this is going to return an int, which is the most area a container, most area of water a container can hold. That seems fine. And this is a function to return the container with the highest area to contain water within. Okay, so what do we have to do? We have to, number one, loop through the array of heights. And inside that loop, we have to loop through the other, I'm going to say of bars, the other heights, the heights of the other bars, calculate the area return max area. So that's kind of our roadmap here. So let's define our loops. So here we're going to do for let I equal 0, I is less than r dot length, I plus plus, and then within it we're going to say for let j equal 0, j is less than r dot length, j plus plus. And already I'm going to make an update because we don't want to compare bars with themselves. That will give us faulty information. So we're going to initialize j at whatever I is plus 1. Remember, we don't have to look at what comes before that first pointer because we've already covered it. So we're always going to be looking at one past j. So first, let's kind of define what we're looking at I and j. So the first thing we're looking at is the height at the first pointer, and that's going to be r at I. So our first pointer is going to be looking at the array of heights at that index. Remember, the index is going to be used to calculate the width, but when we're accessing the element at I, that represents the height of that bar. So we're going to do the same thing for the second pointer. So we're going to say height at the second pointer, and that's going to be r at j. So now we have those variables that will help keep us sane while we write the rest of the logic. So first we're going to find the minimum height between those two. So that's easy. We're going to say the height is going to be math.min, height at the first pointer, and height at the second pointer. Again, pretty straightforward. Then we're going to calculate the width. So we're going to say const width, and that is going to be j minus I. Because remember, the indices is what determines the width. So in the graph, the graph showed everything starting at 1, so we added 1 to the index to figure out where it was on that graph. We don't need to worry about that here because everything is shifted to the shifted down because we're just working with the array. So the width is j minus I. So the current area is going to be pretty easy, the height times the width. And then we're just going to capture this somewhere because afterwards we're going to go through and we're going to find the maximum area. So we're going to have to capture each area along the way. So let's capture that up here. We're going to say const areas, and that's going to be just an object. I'm going to move these so it is clearer. Calculate the area, and then we're going to return the max area. Okay, wonderful. So let's capture this current area. So we are going to say areas at, and then I'm going to make a very long, string with some variable interpolations because we want to know what we're looking at when we see our areas, and we have to keep track of both the index that the bar is at and the height that the bar is at, so we know the difference between the areas. So actually, that's really not true. That's only so we can look at the areas and understand what we're looking at. As far as the code, we can actually just collect the areas in an array and then math.max that. So, that's a little simpler. So I am going to collect the areas in an object so we can look at them, but I'm just going to collect our areas for perusing, and then we're just going to capture the areas in an array. So I hope you all followed that, but you will as soon as we finish this up. So we're going to say areas.push area. And then for our areas to peruse, we are going to do that long interpolated string. So the first thing we're going to do is I'm going to wrap coordinates in brackets. So we're going to mark this as the XY coordinates of each bar. So the first X of the first bar is going to be I, right? Because I represents, meaning the index represents where it is at the X level. And then its Y coordinate is going to be the height at the first pointer. Height at the first pointer. So this is the coordinates of our first bar that we're looking at. And then for the coordinates of our second bar that we're looking at, that is going to be J. And the height at the second pointer. So that all looks good to me. So we are setting this, um, this is the key, right? And we are setting that equal to our value, which is cur area. Okay, so we're going to console.log the areas for, what did I call it? Yeah, areas for perusing. I don't know why it's not coming up as like autocomplete here. And then we are going to return math.max, and we're just going to pass in the areas. And that should be how we get our 49. So let's try that out. Node most water, reference area is not defined, and that is on 19. That is on 30. Where is that? Areas.push area. So we want to do cur area. Okay, easy fix. Let's try that again. Okay, so not a number. Why is that not a number? Probably because we have to spread this, right? Because you don't just pass in an array to math.max. You have to pass in, elements delineated by a comma. Let's try this one more time, and we get 49, which is what we expect. Wonderful. So let's just look at this areas for perusing just for fun to make sure that we our logic is solid. So our first bar we're looking at is at the xy coordinates of 0 and 1, and our second one is at 1 and 8. So 1 will be our constraining height. It is 1 minus 0 away from each other, which is 1. 1 times 1 is 1. Let's look at one further down. Let's look at this one. So here we have a bar that's at 2 and a bar that's at 6. The first one has a height of 6. The second one has a height of 8. Our constraining height is going to be 6. 6 minus 2 to get the width is 4. 6 times 4 is 24. So this is what we expect. Again, this is a great solution, except it is a big O of n squared, which is not great. I wish I could put a down emoji in my code. I mean, for more than just this problem, right? So we're going to now talk about a more optimal solution, and we're going to talk through it. It uses a two-pointer design pattern. So if that is a hint for you, then go try and solve it yourself. Otherwise, keep watching. Okay, so we are going to move in to talking about our two-pointer approach. So this approach involves initializing 2 pointers at the start and end of the array. These 2 pointers signify the max distance between the bars. So again, if you can imagine, you have pointer at bar 1, pointer at bar 2. That is the maximum width of a container. If the bar on the left's height is less than the bar on the right's height, we move our left pointer up 1. If the bar on the left's height is greater than the bar on the right's height, we move our right pointer down. So in this way, we maintain the largest width we can possibly get, and we find the bars that have the maximum minimum height of a bar to find the largest area that water can be in. So that doesn't make any sense. We're going to walk through a visualization, and I hope that clarifies what I'm talking about. So here's our lovely bar graph, and we initialize our 2 pointers. So our first pointer is at the first bar, our second pointer is at the last bar. So we fill it with water. What do we get? So we are constrained by the first bar, which is of height 1, and our last bar, which is at index 9. So 9 minus 1 is 8. 1 times 8 is 8. Great. So this pointer, the height of the bar is lower than this pointer. So to find a container or a potential container with the capacity for more water, we have to move this one up. So we lose some width, but we're hoping to gain some height. So let's see that happen. So again, this is the formula for our height. So we move our first pointer up, and now we are dealing with the constraining height is here, which is 7, and these bars are 7 places away from each other. So with that, we get 7 times 7, which is 49. So our right pointer is now lower than our left pointer, so we move our right pointer down. Here we have a constraint of 3, so it's 3 times 6, which is the distance away, and we get 18. And let's do it one more time. We now have our second pointer is at 8. These bars are 5 widths away, so we have 8 times 5, which is 40. And again, I think it's interesting and something to really understand is that you can't just look for the highest bars because that extra width makes a big difference. 49 is a lot bigger than 40. And so yeah, that's like a piece of this problem that I didn't initially realize when I first looked at it. So in this way, we are able to capture that largest area, maintaining the greatest width we can get, and then continuing to try and find the largest bars that we can find to make the combination to get the largest area. So let's code this out. All right, so we are going to code out this optimal solution. So let's call this function max water. It's going to take our array of water, and honestly, we can just copy the code block from the comment block from up here. Easy peasy. All right, so what do we have to do? We have to initialize our 2 pointers. And then we have to essentially move them closer together until they meet, right? Because when they meet, we've looked at all of the possible widths and height combinations, but we don't have to look at every single combination because, again, we are maintaining that maximum width and kind of only looking at the heights that go with the maximum widths. We also want to keep track of our max area, right? So each time we find an area, we want to update our max area and then return that max area. So this is pretty simple. We're going to initialize a while loop, and this is, first we're going to initialize our pointers. So let's say let max area equal 0 to start, and then let's say left equal 0 and let right equal r dot length minus 1. Okay, so while left is less than right, what are we going to do? We're going to calculate our area, which is going to be exactly the same as the function above it. So we're going to say let height equal math.min, our array at left, and our array at right. And that is going to be our height, and we're going to let the width be right minus left. That's going to be our width. And then our current area is going to be height times width. Very simple. And then we are going to update our max area. Max area is going to need math.max, max area with our current area. And then finally, we're going to decide which pointer we are going to move. So if the array at left is greater than the array at right, we are going to move our right pointer down. Again, we are moving the pointer that is at the bar with the lower height. So that's how that works. And then else, we are going to move our left pointer up. And I think that is it. We're going to return our max area. And yeah, let's see if this works. So let's just change this to be the optimal. And run this. Most water is not defined. Why not? Oh, because I called it max water. So let's change this to max water. Try one more time. Okay, and we get 49 as expected. So yeah, and because we are only actually looping through this array once, right? The left is taking care of the left side of the array, the right is taking care of the right side of the array, and meeting in the middle, we're actually only looking at every element once. This is going to be a big O of n, which we like much better. This is obviously the more optimal solution. All right, that's our video. I hope you all enjoyed this. I think it's actually one of those problems that once you understand the two-pointer approach is actually pretty simple. I know the code is pretty simple, and once you kind of get that, it's relatively easy to write. So the real key thing I want to highlight here is the importance of understanding your patterns and where to apply those patterns. So when you get a problem like this, you can say immediately, the two-pointer approach. So that's that. I'll see you all soon.